Hello again. Today I'm going to discuss the most beautiful science experiment ever undertaken. That's what it's called. That's not me calling it. The double slit. And I think the main reason why it is so popular and amazing and famous and beautiful is that you can explain it very easily what happens. So it's not convoluted what's actually happening. And what is happening is truly amazing. And that can be proven very easily. And to this day, we still don't know what's going on. That's after 100 years, including the likes of Einstein, Niels Bohr, and Dirac, and all these Feynman, and all these incredible, wonderful physicists have not been able to crack the nut on quantum physics and what exactly is going on, especially with the double slit. But let me just explain the double slit a bit more. It was actually first done by Thomas Young in 1801. So that's how far we're going back. Well, of course, the equipment was, by today's standards, very, very primitive. The question was, and the question had been asked for many years, is light a wave, like sound or water? Or is it a particle, like a bullet? And going back to Newton's day, Isaac Newton invented what was called a corpuscle at that moment in time, thinking that it was a particle. But Thomas Young set up the double slit in 1801 or 1805, one of those dates. And what he did was very basic. He just aimed a small array of light as he possibly could into a call it a cardboard slot with two slits in it. So it's a cardboard poster with two slits in it, and then a receiving cardboard poster behind that, so that they could see where the light was coming after going through the two slits. And it wasn't amazing at that time, but what happened was he shone the light, it went through the two slits, and then what we had at the back was an interference pattern. Now let me explain. There were two patterns, a clump pattern and an interference pattern. The clump pattern is what you would see is, let's just imagine you are firing bullets, real life bullets, through a great big board with two slits in it. You'd expect, after shooting 1,000 bullets, oscillating to and fro, you would expect two vertical lines to be or vertical lines of bullet holes to be in the receiver poster at the back. If you were pushing water waves through the two slits, they would interfere with each other, and then when it actually touched the receiving poster at the back, it would actually have a number of vertical lines, the most dense being in the middle. And that's called an interference pattern. So you've got interference, wave, clump, bullet. And if Newton was right at that time, it would have been a clump pattern, but actually it was an interference pattern. So Thomas Young did a lap around the laboratory, waving his hands, and for 100 years, people assumed light was a wave. Excuse me. Quite simply, it was over and out. Look at the interference pattern at the back. And then, in something like 1905, I think that's the Annus Miraculous from Einstein. He did 5 eminent papers in the 1 year. Most physicists do one in a lifetime. He did special relativity, Brownian movement, the the photoelectric effect, which is what I'm going to refer to now, which actually is the only one he got a PhD for. The photoelectric effect was really interesting. He was shooting light at certain wavelengths. A wavelength of light is just a color. So they were shooting wavelengths of light at a metal, and thereby dislodging electrons. But no matter how intense he made the wave, the amount of electrons displaced was always the same. That proved that the energy in the light was quantized. It came in specific packets, which he called, and we do today, call photons. Now, Einstein never said, "Oh my God, Thomas Young, you're an idiot." Number one, he wouldn't say that because he'd already died 40, 50 years earlier. But also, the double slit experiment had been reproduced many, many, many times. So there was no question it was a wave. But now, there was no question that it was a particle with a photoelectric effect. This was a genuine paradox. And it really did, for a number of years, cause great consternation in the scientific community. It can't be both. How can light be both? It can't depend on how you measure it or observe it, or can it? And in point of fact, that was proven by advances in the double slit, that in point of fact, it is the measurement and the observation and the way you look at it, whether you choose to measure it or not, that dictates the fundamental nature of that light. Okay, but let me... so this is called wave-particle duality, which is an amazing thing that only happens in the quantum world. What you've got to remember, in the quantum world, everything that happens in the quantum world is counterintuitive to our classical Newtonian world. That's what makes it so wonderful and so exciting. We use words like observe and measure, but really, they're not the right words, because what we're observing and measuring is something we're not used to. But let's get back to the experiment. Equipment got more sophisticated, and then we were able to fire a photon at a time into the double slit. And that was very important, because that meant at the back poster, over time, it would show us a pattern. And what happened was, the scientists of the day, and we're talking about the 1940s, 50s now, the scientists of the day wanted to actually observe which slit the photon was going through. Because in order to get that interference pattern, the photon had to literally split into two and then interfere with itself, which is very strange. But the whole thing is strange. So the scientists put down a very, very special light detecting camera to spot which slit the photon was going through and what was happening. And then an amazing thing happened. This is absolutely amazing. What happened was, when the camera was there on the back receiving poster, when the camera was looking, the clump pattern came back. When we looked away, there was an interference pattern. And it's that black and white. Move the camera, interference pattern. Put it back, clump pattern. How does this, again, get under your fingernail, get a little bit of dust, put it on your finger, and how can something a million times smaller than that know whether it's being observed or not? This was amazing. This was absolutely unbelievable. It was not what was expected. And classical physics was thrown out the window. Did not apply at the quantum level. So, what they did then was they thought, hold on a minute, maybe the camera, which is detecting the light, is actually interfering with that light, which actually it does. By having a detector, you bounce off the photon. Now look, that didn't explain why it would so neatly go from an interference pattern of multiple lines to a clump pattern. That didn't explain that, but it might explain something. And then a bright spark said, well, hold on, why don't we shoot one photon or shoot a string of photons, but from a place where we know exactly where it's going to go, exactly where it's going to hit, and have no camera detection there, because we don't really need to. We're not measuring it. We're not taking photographs of it. We're not interfering with it. We just know where it's going. And believe it or not, the patterns kept on changing. If we didn't know where it was going, there was an interference pattern. But if we knew where it was going, the interference pattern changed to a clump pattern. This is called collapsing the wave function. So, going from an interference to a clump is collapsing the wave function. It's where this wave, and it's not a physical wave, it's a probability wave, but we can talk about that later. But it goes from being a wave with wave-like properties to a particle, to a thing. Is this how life was created, where we observed at the beginning? Where we go beyond the universe, is there nothing until it's observed? There's a thing called the observer effect, which believes this, and there's a lot of experimental data to justify it. So maybe things only come into existence when we see it. Einstein and a lot of people said that this was a load of rubbish, and he did what's called the EPR paradox, which poo-pooed all of this. But then in the 60s, Einstein was shown to be wrong. Einstein famously called quantum entanglement. Einstein famously called quantum entanglement, which is slightly different. We'll discuss that too. He called it spooky action at a distance. But no matter what, no one knew what was going on. And the fact that if we know where it's going, and if we don't know where it's going, why should that collapse the wave function when we know where it's going? Truly amazing. After the double slit, there was an experiment then called, which I'll go into in the next lecture, the delayed choice quantum eraser experiment, which did two things. Number one, it proved that the wave function is collapsed when we know where it's going, and that was proven beyond doubt in the delayed choice. I mean, it was, it's conclusive. It's never been wrong, by the way. It's always worked this way. It's never once not gone to a clump pattern. And this is where we talk about nature. It looks like nature is deliberately not letting us know. Our equipment is advanced enough that we can measure at the photon, even, at the subphoton. A photon isn't an empirical unit. It's a fundamental unit, so you can't have half of one, but it's quantized. That's the whole point. But we can we can see the photon and detect it clearly. So we have the measurements to do it, but then nature changes the ground rules. It sort of says, if you know, if it's possible that you should know, I don't care if you're looking or not, but if it's possible that you could know, then I'm going to collapse the wave function. So it just beggars belief. And the experiment has been repeated many times with always the same result. And we don't know why. We don't know why when there is an observer or a measurement taken or a potential measurement taken, the wave function is collapsed. Now, there are some other studies into consciousness and the wave function and collapsing the wave function. Now, everything I've told you is absolutely 100% validated by scientific experiments. There's no question what I've told you happens. The studies into quantum consciousness are in its infancy, but some groups have done a lot of research into it, and I'll put the link, because I forget it at the moment, the Noetic Group Institution, something like that, but I'll put it in the link below, has done a lot of work on consciousness. And what they first did was they said, okay, you can collapse the function, but can a meditator in a different room, just by thinking, on his computer there's a little light that goes from red to green. When it's on green, he has to imagine which slit the photon's going through. And when it's on red, he can relax. Now, if you believe their results, and they say they have over 10 gigabytes, I do recommend you look up the site. They say that meditators could collapse the wave function much more than ordinary people. Cut a long story short, what they did next was they did it over the internet. So they set up a Linux experiment, and it was 4,000 miles away in South Africa somewhere. And the meditators meditated, same thing, when light went from red to green, they meditated and they collapsed the wave function. And the reality is, if you believe the data, when there was a Linux software sending the data, the wave function did not collapse. When it was just a program simulating a meditator, but when it was a meditator, it did. Now that's very strange, because the data is essentially same, because the Linux software is basically simulating data from meditators over time. It's like this little, what I call the fingernail speck. How could the fingernail speck know whether there's a human on the internet 4,000 miles away or just software? And it's crazy. I have a scientific mind, and I like to think, nah, come on, that's not happening, it's not true. I'm not going to say that until I know what the real answer is. And we don't know. Science doesn't know. And until we know, I don't think it's fair to say to these other people who look, spiritualists and people who look into consciousness, and religious people and meditation specifically. I don't think it's fair to say that they don't, they're wrong, because we don't know. I hope you've enjoyed that insight into the double slit. I've put some links there that you can link to. Look, if you Google double slit, it's all over the place. Same with the delayed choice quantum eraser, which I'll explain next lecture. And that's really fantastic. The delayed choice is obviously a bit more complex. It includes entanglement, but what it will prove is that events that have already occurred can still be altered. And John Wheeler, the great physicist John Wheeler, believes that this applies to a photon coming from a distant galaxy that has traveled There's a thing called gravitational lensing that I think I'm right in saying Einstein came up with. But a photon has to go to the left or the right of a huge galaxy. So for billions of years it could have gone to the left. But how we choose to measure it when it comes to us can determine whether it actually went left or went right. So even though it's traveled for a billion years, that can all be rewritten. I know it's crazy, but that's why you're doing this course. The beauty of it is, quantum computing can take advantage of this superpositioning and also quantum entanglement and quantum tunneling. And quantum tunneling in conjunction with quantum entanglement, they believe now there's a lot of experimental data showing that the monarch butterfly and birds can migrate. Something we've never understood, in quantum biology, very interesting. We've never understood, how did they get to the same place thousands of miles away and mate and there for half an hour and then come back? We believe it's always been the magnetism of the Earth, but obviously that's not enough by itself. It's so weak. But quantum biology is teaching that now, and that's the subject of a different course. But quantum biology uses superpositioning, quantum entanglement, and quantum tunneling. We don't know how it works, but we can harness it. That's why it's exponential. That's why in certain tasks it is 1,000 million times quicker than today's supercomputer. Talk to you soon.